So we have actually made quite good progress in terms of, let's call it now, standard methods that we can use for incomplete data. So we began with direct likelihood or ignorable likelihood with as companion direct Bayesian or ignorable Bayesian analysis, which basically saves, under the assumption of missing at random, all likelihood or Bayesian methods, for which we need a fully specified model. In chapter 33, in the previous chapter, we discussed weighted estimating equations, which is an extension, a modification, if you wish, of standard estimating equations, standard generalized estimating equations, to the situation where you assume missingness to be missing at random. So it kind of looks like we have covered most methods, but that's of course not entirely true. There are a number of situations that, if you think about it now, we haven't covered. For example, what if also covariates are incomplete? Because in the direct likelihood framework, we have really reflected on dropout in a longitudinal setting in the outcome variable. What about covariates? That's one thing. And then, yes, generalized estimating equations, that's a frequentist technique, but there are many others. We could, for example, be interested in conducting, let's say, a Fisher's exact test, which is frequentist, or Cochran-Mantel-Haenszel, or all sorts of things. For example, you may also want to do, in a longitudinal study, a comparison between two treatment arms at the end of the study. So just a comparison in terms of the last time point. To make it concrete, we may want to do a t-test at the very end of the study. But of course, in a longitudinal context with dropout, if that last time point is not available, but earlier time points are, ignorable likelihood implies that you have to analyze the entire longitudinal sequence so that the predictive distribution can actually use information on incomplete subjects also at the last time point. The bottom line is, if you're interested in a simple test at the last time point, with incomplete data, you do have to analyze the entire longitudinal sequence. In all of these and many more cases, multiple imputation, which was invented by Rubin, formulated by Rubin in the late 70s, 80s of the previous century, Rubin has proposed multiple imputation as a technique to essentially separate out the handling of the incomplete data issue on the one hand, and the data analysis that you would conduct anyway on the other hand. Okay, so what we are going to do in this chapter is provide a general idea about how multiple imputation works. As we go, provide a bit more detail so that we can have also an idea of how it technically works. And when that's done, we will illustrate it and discuss in particular its use in practice. So at the end of the chapter, it's a good idea to really think about when am I in practice going to use what technique. Sometimes there is overlap between the techniques you could use. Sometimes there may be, in your mind, and that may be different from my mind, a clear winner as to the best way forward. But again, it's good to have a good perspective. When would I, for example, prefer a direct likelihood, an ignorable likelihood method? When would I prefer generalized estimating equations? So that means weighted estimating equations. And then finally, when would I rather do multiple imputation? When all of that is set, we still have to recognize that we haven't covered missing not at random, and then not in the next chapter yet, but soon thereafter, we will move to missing not at random, i.e. sensitivity analysis. So without further ado, let's move into multiple imputation. The general idea is, if you have a missing data point and you impute a value, so you fill in a value, you treat that value as if it were data, and that's not correct. That's actually, in a way, scientific fraud. Of course not if you clearly report that you have done that, that's a different matter, but it doesn't make it any better. One. So we are going to impute more than once, because imputing more than once actually means that you can keep a handle on what you know, the signal, and what you don't know, the noise, the uncertainty. In other words, if you have a longitudinal setting with a measurement taken, a measurement not taken, and then a measurement taken again, and let's assume this is a growth curve of total body length of human children. Why am I giving that example? Well, that's one where there is an awful amount of precision. And there is not so much variability. I mean, your body length is not going to be one day 3 centimeters more than the next day. It's a fairly stable measure. It's something that you can measure very precisely. And it's also something that, as such, biologically doesn't vary all that much unless over a longer time frame, at least for human beings. So that means if there is a value missing, intuitively, without even thinking about any of the methodology that we have developed and are developing now, we could say, okay, maybe something like that is a good prediction. Of course, we are not totally measurement error-free, and yes, there is a little bit of biological variation. So if we now say we have to acknowledge that this is a prediction, that prediction has 2 sources of uncertainty. First, it's based on the rest of the data, right? Because maybe I have formulated a straight line, maybe I have formulated a random effects model, something like that, just think about it. But that is not done on an infinite amount of data. We only do that on a finite amount of data, so the parameters involved in the prediction are also estimated with error, with uncertainty. And then there is a little bit of measurement error. So all of that means that this predictive model is not 100% stable. And if I would draw from the so-called predictive distribution, I would have values that vary slightly. There are other contexts, for example, in HIV, where I would measure viral load, or a more classical example, CD4 count, T4 cells, which is a very volatile, a very variable measure, then the situation might be completely different. It's perfectly possible that today I'm here, tomorrow I'm there, then I miss a day and then I'm there again, and the question is, what is it now? Now the predictive distribution in this case may be more variable, maybe more uncertain, so if I draw from it, I may have a larger range of values. And that's the idea. By having a range of values, I can keep the signal and the noise separate and make sure that by filling in, I still don't pretend that I have more information than I really do. So here is the thing. We built a predictive model, and the details of that will follow later to some extent. Once I have a predictive model, I draw from it a certain number of times, m times in our notation, and that m can be 5, can be 10, can be 20, can be 73, but we'll have to think a little bit about what is now a reasonable number. And then we do that, and we have not a single incomplete data set anymore. Well, we still have it, of course. We keep the original version, be sure of that. But then we have also m, let's say 10, for the sake of ease of speech. We have 10 fully complete data sets that are all identical in the observed data points, but vary a little bit or more or a lot, depending on the situation, in the missing data points. But these are complete data sets. So in the second step, I can analyze these data sets in exactly the way I want. For example, I can calculate or I can estimate a treatment effect at the last time point, together with a standard error. Okay, but then I have 10 parameter estimates, 10 treatment effects, and 10 standard errors to that treatment effect. So at the very end, I'm going to combine these 10 different values into a single inference. That means a single estimate and a single standard error. And that is using so-called Rubin's rules. That's what we call Rubin's rules. Rubin developed a method and wrote a book about it in 1987, which maybe was very early in the time frame for a synthesis. If you develop a method and you write a synthesis immediately, you haven't seen, let's say, all aspects, you haven't seen all corners of the room yet. So later texts and also later versions of the Little and Rubin book, but also Rubin and Schenker earlier on. But there are many texts right now. There is the book by Carpenter and Kenworth. There is the book by Stefan Buren, focusing on multiple imputation in a very present-day context. These books were written a few years ago, meaning that they're very accurate and up to date. So that's where it comes from. Now, the method was actually created in part because Rubin was working at the Bureau of Census in the United States, and the idea was, okay, the census is incomplete. We have many end users. Many people will use the data set in the end. So we should find a method where we can handle the missingness centrally early on, and then we send out the treated data sets, and it will be easier for people in the field with different levels of statistical knowledge and sophistication and software to analyze these data. So that's where this idea comes from. But the side effect was that the number of imputations shouldn't be too large. And this method was created at the time that, for example, also the bootstrap was invented. Now, for those people who are familiar with bootstrap, there we easily talk about 1,000 replications, etc. Rubin wanted a method that would work with a lower number of imputations, with lower numbers of replications. So that's where I would call it the myth comes from, that the number of imputations should be 5. It shouldn't be 5, but it has been stated by Rubin, by Little, that in many cases something as small as m is equal to 5 works. It's even true that in the original book there is reference to m is equal to 2. Why? M is equal to 2 means more than 1, means as soon as you have a number of missing data points, but each of them is generated, predicted twice with error, with noise on it, you have a handle on the uncertainty. Only m is equal to 1 doesn't work, because then you don't have the tools that you need to take the uncertainty into account. Nowadays, of course, with modern computational tools, m can be a bit larger. So we shouldn't really procrastinate over should m now be 5 or 10 and think about it for hours and days. Just do it. Run it with m is equal to 5, run it with m is equal to 10, with 15, and see whether the results stabilize. That's something you can do. But the thing is, and there is actually mathematical evidence for that, m doesn't need to be 100 or 1,000 in most applications, because the convergence to the maximal information you can extract from the data is very quick. Yes, going from 2 to 3 imputations can be an important gain of precision. But no, going from 12 to 13, you don't see that anymore. So it really plateaus relatively quickly. So to summarize, in this graph we see we have the incomplete observed data. For example, if m is equal to 5, we impute that data set 5 times. Once we have the 5 data sets, we apply the same mixed model, the same t-test at the end, the same whatever analysis you have in mind, as exactly as you would do had there been no missing data problem, which gives you 5 results, usually but not always, taking the form of parameter estimate and standard error, and these are then in the final step combined into an overall inference. So, I will go over this again, but in this section I will actually do this slightly more technically. So, what we basically look at is the predictive distribution. So we have an initial model, and that initial model usually is not the model we are finally going to use for analysis, but a very rich model. Think of a multivariate normal model without too many restrictions and constraints. So you take your data set, everything is continuous for the time being, you formulate a big multivariate normal model, and from that model, for a given subject, for a given sequence, longitudinal sequence, for example, you look at the predictive distribution, which is always the distribution of what you don't have given what you have. And for the record also, given covariates. But since you have fitted a model with, for example, a multivariate normal with mean and variance parameters, these are also estimated. And that estimation is usually done on a finite data set, so it's not infinitely precise. There is error on those parameters. You have a standard error for those parameters already. So you don't know the true model, you estimate that working model. It's a working model, just as in weighted GE, you also have a working model first before you finally go to your data analysis model. So, Bayesians would draw from the posterior distribution of that theta parameters. Likelihoodists can say, likelihood people can say, okay, I have my parameter, I have its standard error, assume normality for the time being, so you draw from that parameter a number of time. So, let's say theta star is one draw. And of course, we're going to do it 5 or 10 or 15 times, but let's just illustrate it for one for now. So once you have your parameter, you fill that in, and then you draw YIM. So you draw the missing data from the predictive distribution. Okay. And now we do that same thing capital M times. We repeat that, so we get a parameter and all the missing data are filled. We start again, we draw a parameter, all the missing data are filled in, and again, and again, and again, until we have our 10 copies, for example. Okay, then you fit a model exactly as you want. And that model is going to produce a parameter which I will now distinguish from theta as beta. For example, you fitted a multivariate normal model on the incomplete data. You have your 10 incomplete data sets. But now you fit, for example, a linear mixed model. That linear mixed model produces a treatment by time interaction. Let's say that's your sole parameter of interest. Fine, so your beta is then going to be the treatment by time interaction. Only you have that beta m times. You have it a certain number of times, and that's what we have here. But not just the beta, there is also the standard error to that beta, or the square, the variance to that beta. Of course, I'm explaining it for a single parameter, but you can do exactly the same for a whole vector of parameters, right? And then you have a parameter vector at every stage, and you have the corresponding variance-covariance matrix. Good. Now, then in the third stage, the pooling rules are applied. But for the parameter, they're remarkably simple. You could have guessed it. Huh? If you thought, hey, it can be that simple, it cannot be that simple. Yes, it is that simple. You take the parameters, all 10 parameter vectors, and you calculate their average. Done. That is your final estimate. For the precision, though, it's slightly more complicated, but only slightly so. And why is that? Well, each of the 10 data sets are imputed. That's the whole point. But that means every one of the data sets contains more information than it should have. And by averaging the standard error or the variance-covariance matrices, that's not going to go away, because if 10 standard errors are too big, or 10 variances are too small, rather, the average is going to be too small. So that is why, yes, we average, but that's only one of the two components. That's the within imputation variability. But then we say, how can we now see what the impact is of missingness? Well, the very simple and intuitive and clever device is the between variability. And that is, you take your individual parameter vector, so data set specific for each one of the 10 data sets. That is beta m. In the meantime, we have the average parameter vector, and we just see how much do the parameters fluctuate, how much do they fluctuate around the average. It's immediately clear. If there would be no missing data and you would do this exercise, well, first, it's useless. There's no need to impute a data set that's complete. But if you would try to do, there would be nothing to impute, and your 10 data sets would be identical. That would mean your 10 beta m's would be identical. And that would mean that they're equal to their average, and then the between variability would go away. If, on the other hand, there is just a little bit of data and a huge amount of missingness, the prediction will be very uncertain, and your beta m's will be very different from each other. The between variability will be very large. So, This actually tells us on the side that we have a handle on what information is observed and what information is missing. So the total information is the sum of the two. The within variability produces the information, or the uncertainty rather, that you have on the complete data sets, had the data sets been complete. And how can that within variability disappear? Only by having the sample size going to infinity, right? If you have more and more data, so a bigger and bigger and bigger data set to begin with, then in the end, the within variability is going to disappear. But even then, if you would have an infinitely large data set, of which 50% of the data are missing, the between variability would still indicate that there is uncertainty. There's half of the data that you don't know, and that doesn't go away. So there are these two sample sizes. There is N and there is M. M is the classical sample size we have with complete data, M is the number of imputations, and that in itself is something that also can go to infinity. Okay, that is now important for the next subtopic, and that is hypothesis testing, because yeah, many hypothesis tests that we do are either exact, like F-tests in normal theory, with linear regression, with multivariate linear regression, even to some extent, but there are also approximations in linear mixed models. But if that doesn't work, like with categorical data, we use chi-squares, for example, which is an asymptotic result. The thing is here, in this setting, as I just said, N can go to infinity, but it doesn't mean M goes to infinity. So if N and M goes to infinity both, then you are back to a full asymptotic situation. If N is large but M is small, then Lee, Regan-Nathan, and Rubin produced a testing framework that acknowledges the fact that you have only a finite number of imputations. And they do that by an approximate F-test, a little bit like Satterthwaite and Kenworth-Roger have also done. So here I will not go through the details. It's not important. The only thing we should see is that if you're a software developer, all the tools are there to actually calculate your test statistic and refer it to the correct distribution. It can be done, and it's implemented, for example, in SAS. Okay, how do we now do this in practice? Well, you may say, you already explained that, right? And I did in a way. If I back up a few slides, yeah, there is the imputation task, the analysis task, and then the combination task, or steps, but there are three. And now the question is, how on earth does this work in a software tool? Well, the thing is, no matter what software tool you use, you need 3 procedures in SAS, for example. You need 3 functions in R, for example. And in SAS, it works as follows. ProcMI is designed for categorical data, for continuous data, for a combination of the two to create imputations. Once that's done, you have your output data set, which is, for example, 10 copies of the input data set, but imputed. And then you run that through whatever analysis tool you want. Of course, ProcMyFavorite doesn't exist. I hope that's clear. But this could be ProcMixed if you want to run a linear mixed model. It could be ProcReg if you want to do a simple linear regression. It could be ProcANOVA, ProcT-test, Proc whatever. And then at the end of the day, we have to save the output, we have to save the parameter estimates, the precision of those parameter estimates, of course, and that is then fed into the inference task. ProcMI Analyze combines everything into a single analysis. Okay, so if you remember the analysis of the orthodontic row data set, we have done that using a few simple methods, but also using ignorable likelihood, using direct likelihood. And if we apply model 1, again, remember, that's a broken line for boys with 4 points, a broken line for girls also with 4 points, and an unstructured 10-parameter variance-covariance matrix. Well, if you do that with multiple imputation or direct likelihood, you get not exactly the same result, you get a similar result. But we do see with m is equal to 5 here that there is still a little bit of extra uncertainty a precision loss. You can estimate the parameters that you want, you can construct confidence intervals from it, etc. But let's now switch to the age-related macular degeneration trial, which in the continuous case we have analyzed before. We've seen the data set, for example, in weighted estimating equations. And, well, if we analyze the binary data, here is a question. Hey, we have done this with weighted estimating equations. Wasn't that good enough? Well, what we did see in several analyses is we can actually be losing quite a bit of efficiency. So maybe it's interesting to combine multiple imputation with GE. And a follow-up question is, do we still need to use weighted estimating equations? And the answer is no. Weighted estimating equations are used to analyze incomplete, non-Gaussian longitudinal data. Because incomplete longitudinal non-Gaussian data analyzed with GE is only valid under missing completely at random, but we want to upgrade it to missing at random. That we did in the previous chapter. But now, each one of the 10 data sets has been processed. ProcMI, I mean the imputation step, takes care of the missing data problem. What results is, what is turned out is 10 data sets that are all complete, so we can analyze them with standard methods. One question is, how does this perform in terms of efficiency? How does this perform in terms of bias? And another question is, what is now the computational convenience? You will see that nowadays, with ProcGEE on the one hand for weighted GE, with, on the other hand, multiple imputation, it's really not the case that one is very much more difficult than the other one. They're comparable. We'll have to think about it in terms of advantages and disadvantages. So, once again, we are going to fit GE and GLMM. But this is actually a very interesting advantage of multiple imputation. One, I can analyze GE, I can analyze the data with GE, but also with GLMM, next to each other. We don't have to choose a priori which of these guys we are going to prefer. In other words, if I would not have multiple imputation, GEE would mean weighted GE, and GLMM I can use direct likelihood. But that implies that not only the analysis method is different, also the way in which I handle incomplete data is very different. And then it's really hard to see why the differences are the way they are. So, an advantage of multiple imputation is, one, we produce 10 imputed data sets. And then we start to do several analyses on the same data. That's a very important use of multiple imputation, several analyses on the same data. So multiple imputation, GEE, is an important use. Several analyses on the same data is an important use. Incomplete covariates is an important use because you would have incomplete covariates, incomplete outcomes. All is processed at once, and then at the end of the day you can do the analysis that you want. So, okay. Let's now look at the results. What we see, for example, is, well, the GE result, the GLMM results. We're very familiar with that. And you can go back to the part of the course dealing with the relationship between the marginal and the hierarchical parameters. And exactly that applies here as well. So you can say, okay, the GE parameters are smaller in absolute value. They're like 1.7 times smaller, and that applies for all. And we know why. We can interpret that just as we did before, because the missing data problem has been taken away. There is another important advantage, I should say. There's another important advantage of multiple imputation, and that is you can do the imputation on another variable than you're finally using for analysis. In the ARMD data, remember, we have age-related macular degeneration assessed through visual acuity, which is 72 letters, which is continuous, with quasi-continuous. even if we want to analyze the binary outcome, we can do the imputation first on the continuous variable. And then, only then, do we dichotomize. So, for example, in a study on body mass index and overweight or obesity, you may say, I'm interested in the binary variable obese, yes or no. But you do have the body mass index, so the multiple imputation is done using body mass index, and then only then is the data dichotomized. You can even go further and say, well, I will do the imputation on body length and body weight, or maybe body length and the cube root of body weight or something like that. And then I calculate body mass index, and then I dichotomize. So you can really go back to the base variables. Okay, don't do imputation on body length, body weight, and body mass index together, because you will have patients where the formula connecting the two doesn't apply anymore. There is a lot of nonsense written about this. You go back to the base variables if you do either. You work with body mass index, full stop, or you work with body length and body weight, and then the rest is calculated later. Not the two at the same time. That would make no sense. Okay. So, I will be brief and go over the following relatively quickly. How can we now do this in SAS? Well, there are several options available. Usually, it's not something you learn by heart, but it's something you know is there, and when time comes, you look it up, and you remember what are the advantages and disadvantages of the various methods. One aspect that is a source of confusion is monotone. What do we really mean by monotone? Because in ProcMI, it has two different meanings. So, the first major tool, major statement as you wish, is monotone. And monotone, that means the input data are monotone. This doesn't work if you have non-monotone missingness, intermittent missingness. So this is in longitudinal terms for pure dropout. Yeah, but if that's not the case, you use one of the other two that I will discuss in a moment. So what you then can do is say for continuous variables, the predictive distribution, because all the rest is to do with what do we use in terms of predictive distribution? So what do I use to come up with imputations? You can build a predictive model through regression methods, or for binary data, logistic regression, or more generally, discriminant analysis. Or you can do predictive mean matching, and predictive mean matching is more, you look what's available and you pick from it. In other words, you look at a number of people with the same or with similar observed data, but with also the missing data for your subject observed. So let's say subject 7 has the measurement at time 4 missing. You look at many other subjects that are the same in terms of the observed data of subject 7, but that have a value at time 4. And then you draw from those. So that's predictive mean matching. Propensity, that actually is similar, but you work with the conditional probability of assignment to a particular treatment group given a vector of observed covariates. So a propensity score is generated, as we see here, for each variable with missing values. So you basically build, like in weighted generalized estimating equations, the probability for an observation to be missing. And you use that as a tool, also grouping observations, a bit like predictive mean matching, to draw from it using an approximate bootstrap. I'll be brief about it, even though there's a bit more detail in the slides than with the others. It's of limited use when the association between variables is of interest. So I would typically not recommend it. MCMC is the extension of the monotone framework to non-monotone data. So if the input data are non-monotone, you can use MCMC, where the multivariate normal model is considered, but you estimate at first using Monte Carlo methods. And that's the default in SAS. Of course, MCMC works for monotone data as well. But the monotone statement can be considerably faster than the MCMC when the data are truly monotone. So, and then there is a third, more recent addition, which is due to Van Buren. So Stef Van Buren has written a book, and in that book, I think it's with W. In that book, he explains this method. It's full conditional specification. Without doing full justice to the method, let me say it's a little bit like Gibbs sampling. It's a little bit like Gibbs sampling, but adapted to this context. But again, this is not entirely true. It's an analogy, but it's something like that. When is it useful? The data are non-monotone, but that's not a majority of the missingness. In other words, think, for example, of the age-related macular degeneration trial. 80% of the people almost are complete. 20% of the people almost are missing, but missing in a monotone fashion. Now, almost 80 and almost 20 adds up to almost 100%, but not exactly. There are a few percentages of people who have non-monotone missingness. You cannot use monotone unless you throw away these people with intermittent missingness, and that's not very nice to do when you're actually trying to deal properly with missing data. Well, MCMC would really make things way too complicated. So FCS is a method that really is advantageous when you have a lot of monotone missingness, a little bit of non-monotone missingness, as kind of an intermediate between the other two methods. What it does is you start filling in values sequentially. You cycle through a subject, in other words, and you fill in missing values, but you do that repeatedly. You cycle over and over and over again, like Gibbs sampling, and every once in a while, you basically take that observation and you consider it an observation in your imputation. So you draw, in other words, values repeatedly until you have a sufficient number of cycles. The options you can use are the same, but the same as in the monotone case, but the propensity scores method doesn't work. Okay. With that in mind, let's take a look at the SAS code for multiple imputation. The way we begin is we do a little bit of preparation, and there are actually in the books and in the accompanying software tools are there examples of these preparation steps. The thing is that to do the imputation, the data set needs to be organized horizontally. That is, all measurements of a subject need to be in a single line. It's not a typical longitudinal setting where all measurements would be on top of each other with one line per measurement. No, this is one line per subject. So essentially, the preparation before and after is making the data set from vertical horizontal, and then when that's done, you make it vertical again. If you apply this method to, let's say, multivariate incomplete data, these steps are not necessary. You can just work with the input data set. Okay, for the age-related macular degeneration trial, this is the code, and you will agree with me that the code is rather simple. That is also because here I'm happy with the default. I'm not specifying anything, so MCMC will be done. Next, I'm using these variables, and you better specify that, otherwise it uses everything in the data set. But that may be the date, and that may be a lot of irrelevant things. It may be the patient's name, but you shouldn't have that, of course. So all sorts of funny things would happen. No, you specify the set of variables you want to impute. And here in this case, we use the difference with baseline at 4, 12, 24, and 52 weeks. But also lesion, and that's interesting because lesion is actually complete. However, this is a very important point. If you're going to use lesion in your analysis model, it should be part also of the imputation model. Failure to do so is called imputation under the null of no relationship. So, in other words, if you're looking for a relationship with lesion, but you don't include lesion in your model, it will look during imputation that there is no relationship, and then you shouldn't be surprised that you find a very weak relationship later. Yeah, but we want to use lesion, but don't we in particular want to use treatment? Yes, And we also do that because there is the by treatment here. Because treatment is a dichotomous variable, we really use it by treatment. We could do the same for lesion because lesion is actually categorical, but since there is an ordering in that variable, we approximate it. It's a bit of a pragmatic approximation by considering it quasi-continuous. Okay, there is the input data set and there is the output data set. The output data set is 10 times longer than the input data set because we always say there are 10 data sets, and there are logically 10 data sets, but practically they are stored in a single file. So you have a big data set now with blocks, ... That's the first data set, this is the second data set, etc. And they are distinguished by, from one from another by the automatically created variable underscore imputation underscore. So that variable is automatically thrown into your data set. Everything you do later should be done by imputation so that you don't get a single result. Of course, that would be ridiculous, that you get indeed properly the 10 results. Why 10? Because m, the number of imputations, is specified here as n impute is equal to 10. Simple provides some simple statistics so that we can take a look at them. And round, that's to make sure that we are actually talking here about difference in numbers of letters. Okay, we can actually round that to the integer, but that may create certain rounding effects, but we don't need 17 decimal places. So we have chosen here for 0.1. You could write 0.01, then you would have 2 decimal places, etc. And then a key tool is the seed here. The seed serves several purposes. It makes sure that if I run this program and I run it again and again and again, I always generate the same 10 imputations. If there is no seed, there will be an initiation of the random number generator, because after all, we draw from a distribution. That's a random number drawing process, which means that, well, it's stochastic, like MCMC, Gibbs sampling, like Bootstrap. So every time you run it, it's in principle different. But if I encounter a problem, something really weird happens, and I'm unable to ever recreate these data sets, that would be a little sorry. Of course, you can save everything, but that can mean a lot of storage. But by specifying the seed, you're able to specify it ever again. The other thing is, if I do the analysis and I have to report to you, but I run multiple imputation and I find a barely non-significant result, just non-significant, 0.051. I'm tempted to run it again a few times until it's significant, and I say, bingo, I present it to you, I have a significant result. How on earth can you verify that I'm honest and have not been cheating? Well, if we agree before even collecting a single data point that a seed should be specified, this problem is not going to be happening. So that is why we specify a seed. And in clinical trials, the seed may actually be in the statistical analysis plan. It may even be in the protocol. It's agreed between the regulator and the sponsor of the trial, as we say, so everything is nice and verifiable. Then comes the imputation task again, but now using FCS, for example. So here you see how it works. It's easier to see how FCS works in an example than it is in abstract generality. So we start by saying we build a regression model of diff4 on lesion. And after that, we regress. So we progress through the sequence. We regress just as time progresses, 12 on 4 and on lesion, and finally 52 on 4, 12, and 24. We still specify this very same code. And why do we have to do that? Well, otherwise, for example, SAS wouldn't know that lesion is actually treated as a continuous variable, treatment is treated as a binary variable, etc. But that is now the fundamental difference between the previous one and this one. In the previous one, a general multivariate normal model will be estimated at once using MCMC. Here, I cycle through the sequence and build it up as time goes by. in a way, this is very close to the monotone way of proceeding, should it really be monotone, but it is not entirely monotone. That means if, for example, 4 is observed, 12 is missing, and 24 is observed again, well, cycling, monotone would stop. In this case, you cycle through the sequence, 12 is predicted from 4 and lesion, 24 is observed, so nothing to be done, and then you switch to 52, and that is predicted from all of the previous ones. So, here are a few details on the intermediate steps. I don't intend to go over that in detail, but just a few things. Here we prepare the data set for analysis, and we say we actually do the imputation on differences, which is continuous, but then only then are they dichotomized. So we could have done the imputation on the dichotomous data, but the advantage of being able to do it on the continuous data is that you can actually use all the information available and not just a coarse, a rough summary indeed. All right. Then the horizontal data set is translated in a vertical data set. Again, we create the appropriate dummies and so on and so forth. And then comes the analysis task. All right. So in the analysis task, what we see here is GE. So this is done with proc GEE. We have the model statement. No mismodel? No, because we do not need to do weighted generalized estimating equations. Missingness has been taken care of. What is additionally present is the bi-imputation, as I said. So we don't get a single output. We get 10 outputs for each one of the data sets. And those outputs are actually saved through the ODS system. Okay, now, this is where SAS becomes a little complicated because every procedure has its own slightly different way of storing parameters, variance, covariance matrices of parameters, names of parameters, etc. So it may well happen, for example, that you have an intercept that's not used because there is no intercept here. Well, in one part of the output, that parameter may be there, the intercept, with a period, and it's clear to me and to you that it's missing. But in another part, it may simply not be present, and then the matching up is not possible. So usually what we see is the imputation works well, the analysis task works well, and then proc MI analyze doesn't work. And that is because the information that you pass on, even though it's simple, is not exactly in the right format. The best thing is to do print whatever you're feeding to proc MI analyze, and you will see whether the names and the estimates and the precision of the estimates is of exactly the right format. And if not, you need to do something like this. It's problem dependent. It's data dependent, model dependent, analysis tool dependent in general. And then there is the analysis task for GLMM with proc NL mixed, and I'm doing that with proc NL mixed here, just as one of the possible choices, but look in the output. There is an estimate statement. There are parameters in here, but there is also an estimate statement which creates additional parameters. In other words, the base model has a random intercept standard deviation, I should say. But I'm interested also in the variance. So to get that variance, I put everything through the motions also, which is why I save the initial estimates, but that additional estimate is also saved indeed. And then I run proc MI analyze, which is you specify in the model effects all the parameters as they happen to be called in that particular output. I could say, for example, listen, I'm interested in the treatment effect at the last time. Well, in that case, everything intermittently is taken away here, and you just do the final inferences, the combination rules on that single parameters. The same here, for example. It's entirely up to you how to do that. Other than that, what the important bit is what you pass on to the procedure. So this is what I'm passing on to my procedure. And then I have a few additional things like the between, the within, and the total variance covariance that could be interesting to look at sometimes, but it may not be the primary point of interest. Okay, that as far as multiple imputation works in general. There is a specific use where I can use it to transform non-monotone missingness in monotone missingness. So what I've been discussing right now is you have incomplete data, monotone or non-monotone, and you make it complete, full stop. You can also go for an intermediate version where non-monotone missingness is simplified to monotone missingness. But that is the topic of the next chapter.